We left the last segment with a cliffhanger. The electrical signal reaches the end of the axon, but the next neuron isn't touching it. There's a microscopic gap, the synapse. So how does the message cross? The answer is chemistry. When the action potential reaches the end of the axon, it triggers the release of chemical messengers called neurotransmitters. These molecules float across the synaptic gap and bind to receptors on the next neuron, like keys fitting specific locks. If the key fits, it nudges that neuron either toward firing or away from firing. Then to reset the system, the leftover neurotransmitter is cleared away, often by reuptake, where the sending neuron vacuums its chemicals back up for reuse. Hold on to that word reuptake, because it's how some of the most common psychiatric medications work. Now meet a few of the key players, because their names will follow you through the rest of this course. Dopamine is central to reward, motivation, and movement. Too little in certain pathways contributes to Parkinson's disease, and its reward circuitry is deeply involved in addiction. Serotonin shapes mood, sleep, and appetite, and the most widely prescribed antidepressants, the SSRIs, work by blocking serotonin's reuptake, leaving more of it active in the synapse. Acetylcholine drives muscle movement and memory and is notably depleted in Alzheimer's disease. GABA is the brain's main inhibitory messenger, calming neural activity, which is exactly what anti-anxiety drugs and alcohol amplify. Glutamate is its excitatory counterpart, essential for learning. And endorphins are the body's natural painkillers, the source of that runner's high. Here's why this matters so much. Nearly every psychiatric medication and nearly every recreational drug works by tinkering with this chemical handoff, boosting a neurotransmitter, blocking it, mimicking it, or interfering with its cleanup. When we say depression involves serotonin, or that addiction hijacks dopamine, this is the level we're talking about. The mind at its foundation is chemistry in motion across billions of tiny gaps. But individual neurons and synapses don't act alone. They're organized into vast systems with a clear division of labor, a command center, and a network reaching every corner of the body. Understanding that architecture is next, as we zoom out from the single cell to the whole nervous system.